Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. In the today's lecture, we will be discussing the analysis of sequential circuits. In the last lecture, we discussed the flip-flops, and in the current lecture, we will be discussing the analysis of sequential circuits. For the analysis of sequential circuits, what we mean is that what a diagram that consists of certain sequential elements of a circuit represents, or what is the functionality of any given circuits. Suppose we are considering here this example. In this example, we have some flip-flops that are involved in the circuit. So it's representing sequential circuits, although there are some combinational parts involved in it. And always with most of the sequential circuit, there is some combinational part that is involved in the system too. In this system, what we do is we are given certain inputs and we know the current state, and based on these two things we determine the next state of the system and the output of the system. The input here is represented as X here, while the output is represented as Y. The states of the system are represented by two variables. First one is the A and second one is the B. Basically, these A and B are representing the outputs of two D flip-flops. Both of them are positive edge triggered. So basically, D is representing the input to the first flip-flop, while this D is representing the input to the second flip-flop. Both of them are connected through a clock signal because they are sequential circuits. And we are dealing with the clock sequential circuits, so that's why we are representing here the positive edge here in the form of this arrow. So we would see that how we proceed to solve this system or analyze this circuit, that what is its main functionality. To determine its main functionality, the first step that we follow is we write the state equation or the transition equations, as we say. The transition equations generally represents the output or the next output of the flip-flops. So the number of flip-flops that are involved in this system should be written in a form of a certain Boolean expression that represents their functionality at the next clock cycle. Because these are the D flip-flops, so whatever the value of input that is present at this D input would be equal to the output at the next positive edge of the clock. So first what we do is we write the equation of the input of these two flip-flops. The first flip-flop is represented here as A, while the second flip-flop is represented as B. So both of them outputs are the A and B represents the output of the flip-flop A and the flip-flop B. So first what we do is that we write the equation in form of time instants. The T is here representing the time instant. T plus 1 means the value of A at next time instant. It means after the occurrence of positive clock edge, what would be the value of the variable A. This is determined from this expression. You can see that the input here is D, and what the D flip-flop simply do is connect this input to the output after the next positive edge of the clock. If we write it equation, we can see that this is because the sequential circuit, its value is dependent upon X, the input, and also it is have some feedback value which is representing the current state of the system. So the current state is represented by this variable T. So whenever we write the function of T, it means that we are representing the current state value of X or the current state value of A. And when we are writing T plus 1, it means that we are representing the next value after the clock cycle. So if we write this equation, we can easily solve this combinational part here. These are the two AND gates and their result is OR. So we would getting the expression here as AX plus BX. We generally write it as A at time t, X at time t, or with B at time t and X at time t. Similarly, we could also write the expression for the second flip-flop too. The input of the second flip-flop is represented as B, and for the next value, the state value T plus 1, we represent it as A complement X because it is connected through the complement part of the first flip-flop output. And the next thing that is ended with it is the input X. So we write the second equation for the next flip flop as bt plus 1 is equal to a complement at time t into x at time t. Generally, in the form of a more compact waveform, we don't write this separately as function of time at the or representing at the current instant of time. It is understood that it is representing the current time instant, so we can ignore this t here. So if we write both of these equations in a compact form, we can write it as this one, where simply the t plus 1 would be representing the next state, while all the other variables which don't have any value or represented in the form of t, it means that they are at the current state. So in this way we can represent it in a form of this. Similarly, we also have our output in this system. The output here is represented as y, and if you see that this output is also dependent upon the output of these two flip-flops, because first both of their outputs are odd and then they are ended with the inversion of the input. So they are represented in a form of this equation. So in the first part of the analysis, what we do is we just write the state equations or the transition equations of the whole circuit. Now next thing is to form a state transition table or the state table. In a state transition table or the state table, generally we have four kind of sections. The first section represents the present state of the system. Second represents the input of the system. Then we have the next state and the output. Generally the first two sections represents the inputs of the system, you can say, and while the next two are representing the outputs of the system. Because in this system we have two flip-flops involved in it, so both of them are representing a single state. So if we have a combination of two, then we could write four possible combination for each state. It means that we could have either a or b value equal to 0 0 0 1 1 0 and 1 1. And because there is a separate input x here, and x could also have a value of either 0 or 1, if we combine them all, we have basically a 3 input system here. So we would have a total of 8 combinations here. Generally in a sequential circuits with say having m flip-flop and n number of inputs, in a state transition table we would have m plus 1 rows in the state transition table. And how we calculate all these values? First, we have to look at the present state of the value. Say we start with considering that both the outputs of the flip-flop A and flip-flop B are having the value 0 0. So 0 0 here is representing the current state of the system. And for this value, if we are having at state AB equal to 0 0 and an input of 0 occurs, then what would happen is that we simply calculate the next state using these equation. Say for example, for the 0 0 case, if we put the value here a and b equal to 0, what would happen is that because both of them are and both would be equal to 0 and the result would also be equal to 0, so we would get value of a equal to 0. And for the determine the value of b, we would use this equation. In this equation, which is a complement x, so if a is equal to 0, a complement would become 1 and x is equal to 0, then we would have again b equal to 0. So the next state value of b would be equal to 0. And if we calculate the output at the same time, then the output would be equal to also equal to 0, because both of them a and b are equal to 0. So we would get 0 here. Similarly, we calculate all these entries of the table depending upon the value of the present state, which is represented in form of AB, and the value of input that is present in the system. We calculate what is the next state of the value from these equations. Say if we choose now this one, if we have say A equal to 0 and B equal to 1, while X is also equal to 1 here. So in this case, the first we will calculate the value of A here. So because B and X both are equal to 1, so in this case A would be equal to 1, which is here. For the calculating the next state of B, we would use this equation, because the value of A is equal to 0 here and A complement would be equal to 1 and X is also equal to 1, so we will be getting 1 here too. And if we put both of them values equal to 0 1 here, and we have X complement equal to 0 here, that would result in Y equal to 0. So in this way, or you can check all the entries that how we have formed this table. So the second step is that we form a state transition table. The state transition table has four sections. One is the current state or the present state, and then we have the input. And from these two things, we calculate the next state of the system and the output of the system. We could also represent this state transition table in a form of a more compact or specific form, which is generally in this form. This is the same table that we discussed in the last slide. The only difference is that now we have embedded the input variable into the next state and the output section. You can see that the output section and the next state section both have two separate columns now involved in it. We have when x is equal to 0, we would have these next states. When x is equal to 1, we would be having this state. Similarly, what would be the y of output value at x is equal to 0 and x is equal to 1 are also embedded in the same table. So sometimes it is convenient to use this form. The state transition equations remains the same. The table remains the same, only the representation is slightly changed. Now we will be discussing the most important thing of this whole topic, that is how to construct a state diagram. To construct a state diagram, we follow a certain step of sequence. The first step was to have a logic diagram which was given in the circuit diagram form. Then we derived the equations from that circuit, and after deriving the equations from that circuit, we derived a state transition table or a state table. And the last step is to design a state diagram. Because this state diagram is very important because it represents the overall functionality of the system without telling the internal details of the circuitry that is involved in this system. To have a state diagram, first what we do is we represent each state in a form of a circle. Say we draw a circle, and inside that circle we represent the state. The state, because there are two flip-flops involved in this system, A and B, so we have the output of each is represented in form of 2 bits. So for the 2-bit value we have total of 4 combinations. So first we draw 4 different circles, each circle representing a separate state. Say this is 0 0, then this is 0 1, this is 1 0, and this is 1 1. So each circle is representing a separate state. Then what we do is we connect each of the circle through arcs. These arcs are representing the connection between the states, that how different states are connected among each other. For each arc, you see that there are 2 things that are written in form of this format. There is a slash in between. The first thing is the input. This is representing the input value, or in this case the x value. And the second value after the slash is representing the output value. And in this case, this is representing the y value. So from viewing this table, we can easily construct the state transition diagram. For a state transition diagram, first what we do is we draw all these separate states. First we draw the 0 0 here, 0 1 here, 1 0 here, and 1 1 here. And then we look at the input. What is the value of input and what is the effect of this input on the current state? Suppose when we are on the first one, we are on the state 0 0, and we have an input that is equal to 0 occurs. So what would happen is that the next state would be also be 0 0. It means that our system will remain in the same state. So this is represented by this arc here. It is representing the transition that whenever we are at 0 0 state and input 0 occurs, we would remain at the same state. And at that time, because the output value is equal to 0, so this value is representing the output, which will remain equal to 0. So as long as the input remains equal to 0, x is equal to 0, we would remain at this initial state 0 0. Whenever we have x equal to 1 and we are at 0 0 state, what would happen is that our next state would become 0 1. it means that we would move to the value or 0 1 value here, and this is represented as this one. Whenever x is equal to 1, we would move to the next state, which is 0 1. In that case, output still remains the 0, so that is why y is 0 here. Then we again say that if we are at state 0 1, we are say the current state is now at 0 1 here. For the current state to be 0 1 and we have an input value occurs that is equal to 0, then what would happen? Our next state would be equal to again 0 0. So if we are at 0 1 state and as input of 0 occurs, then what would happen is that we would again move back to the original state, that is 0 0, and at that time the output would be equal to 1. So we would be having output equal to 1. So in this way, the whole equation of the system, which is first represented in a form of table, is now represented in a form of a state transition diagram. So each entry here is representing that how our system will behave. So this will be representing the overall behavior of the system, that what our circuit is performing. And if you look at it in more detail by observing the outputs of the system, you will see that basically the circuit that we discussed a few slides ago, from which we have derived this table and this state diagram, it is actually a zero detector system. Zero detector means it will be detecting the value of 0 in say streams of 1, because whenever we have a value of 0 here in input here, the output is asserted or it has a value of 1. Whenever we have 0 here, we would get output equal. So this circuit is actually determining that whenever we have a value of 0 occurring in a stream of ones, we would be having y equal to 1. There could be many other ways to perform this kind of functionality, but for example's sake, we have just taken this sequence detector. There could be many other easier way also that are possible. For representing the flip-flops, what we have seen that we are representing the system outputs, the outputs of each flip-flop in a form of a equation, which is represented in a form of say a Boolean expression. We have represented the input of the system as DA and the input of the second flip-flop as DB. And we have seen that because of the functionality of the D flip-flop, the input is directly connected to the output at the next clock transition. So the value of DA is equal to the value of A T plus 1. Both of them would be equal to the same equation. It means that the input of the D flip-flop is represented here as DA, where a small subscript is representing the representation of the flip-flop. Similarly, B is representing the second flip-flop here. So its equation is here. And the output is represented in form of the whole equation, where A and B here are representing the output of each flip-flop. The A is representing the output of the first flip-flop, while B is representing the output of the second flip-flop. Now we will discuss another example using the D flip-flop. Suppose we are given a sequential circuit of this form. In this form circuit, we have a single flip-flop involved in it, and the output of that flip-flop is represented here as A. The input of the flip-flop, which is D, or you can specifically represent it as DA, is basically the exclusive OR of three things: X, Y, which are the two inputs, and the current state, which is represented as A. So these three exclusive OR terms are representing the input to this flip-flop. Similarly, because of the D flip-flop functionality, the input that occurs here would be equal to the output at the next clock transition or the positive edge. So the equation at T plus 1 would be same as this one. Now, because these are the exclusive OR operation, we can easily form its state transition table. In the state transition table, we have only two states here, 0 and 1, but we have two separate inputs here, X and Y. So if we combine these two inputs with this one, we would have 8 different combinations in the table. For the values of a equal to 0, a is equal to 1, and then each combination of two inputs 0 0 0 1 1 0 and 1 1. So we will have total of 8 different entries in the table, and for the each entry we could calculate the next state or the value of a t plus 1. This next state is actually representing the a t plus 1 here. So how we could calculate it? We simply put the values of a x y in this equation or this equation, and we would be getting the value of the next state. Say if both of all of them are equal to 0, then we would have next state equal to 0, because these are just the exclusive OR operation. And we know that for the exclusive OR operation, if the any input is equal to 1, or we have odd number of input equal to 1, then we would have a or the next value equal to 1. So whenever we have a single one here, we would have output here 1, here 1, similarly here 2, and here. So in this way we form the next state. And the next thing is now to draw the state diagram of the system. In this case, because we have only one state, state out that is represented as a could have either value of 0 or 1. So we would have basically two circles representing each state of this flip-flop output. One is 0 and one is 1. Once we are here and we get the value of input equal to either 0 0 or 1 1, the next state would also remains the 0, means we would remain in the same state. So if we are at current state is 0 and the input occurs are the same, either it is 0 0 or it is 1 1, we would remain at the same state. The transition will occur if we have different inputs, mean x and y are different, then we would move to the next state here, which is equal to 1. And once we are at here the 1, if we have again the values of the input equal to same, means 0 0 or 1 1, then we would remain at the 1 till they are the same. If we have a different value here, then we would move back again to the 0 state. So in this way we design a state diagram for this system. You can see that there is no separate output of this system. That's why we haven't represented something like this slash and 0 thing, because the only output here is the state. So we are not taking any separate state or y value here representing. Is not represent. Also y is also not represented here. Kindly do read these pages for better understanding. Thank you.